Okay, so now let's look at some worded examples. When practicing her tennis serves, the probability that any one of Gemma's serves is in court is 0.3. Gemma serves 4 times. Assuming a binomial distribution, calculate the probability that exactly 2 of these serves are in court. So, this seems like the thing we're going to model. So I'm going to write x equals number of serves that are in court. And then remember, you write it as x is b with number of trials and probability of success. So x is binomially distributed. How many trials are there? Gemma serves 4 times. So that's 4 trials. And the probability of success, what it says, the probability that any one of Gemma serves is in court is 0.3. So 0.3 is our probability of success. And then remembering our formula for the binomial distribution, the probability that x equals x is n choose x multiplied by the probability lowercase p of x multiplied by the probability of failure, which is q, n take away x. Remembering that q equals 1 minus p. So we're trying to find the probability that exactly 2 of these serves are in court. So the probability that x is exactly 2. So we have 4 choose 2 times the probability of success, which is 0.3 to the power of 2. And then q, probability of failure, is 1 minus 0.3, so 0.7 to the power of 4 take away 2, which is 2. You now go to your calculator and you type this all in. So 4 choose 2 times 0.3 to the power of 2 times 0.7 to the power of 2. And you get 0.2646. And that is our final answer. Okay, pens are packed in boxes. There are 6 pens in each box. The probability that any pen is defective is 0.1. A box of pens is picked at random. Find the probability that the box contains exactly 1 defective pen. Give your answer to 3 significant figures. Okay, so in this case, we're looking at defective pens. We're trying to find how many pens are defective. So I'm going to write x equals number of defective pens. And we know x follows the binomial distribution of NP. Well, what is our n and what is our p? Well, there are 6 pens in each box. A box of pens is picked at random, so there's 6 pens, so we have 6 trials. And the probability that any of these 6 pens is a defective is 0.1. And what we're trying to find is the probability that exactly 1 of these pens are defective. So remembering the formula, probability of x equaling x is n choose x times the probability of success to the power of x times the probability of failure to the power of n take away x. So probability of exactly 1 defective pen is 6 choose 1 times 0.1 to the power of 1 times 0.9 to the power of 6 take away 1, which is 5. Now I go to my calculator and I type this all in. 6 choose 1 times 0.1 times 0.9 to the power of 5. And I get 0.354 to 3 significant figures. And our part B, find the probability that the box contains at most 1 defective pen. So this is asking for the probability that x is at most 1. So I'm going to say less than or equal to 1. So that is the same as the probability of x equaling 0 plus the probability of x equaling 1 added together. Does it say to three significant figures? Yes, it does. So first, let's find the probability of x equaling 0. Well, that is 6 choose 0 times the probability of success to the power of 0 times the probability of failure to the power of 6 take away 0, which is the power of 6. So now I go to my calculator. 6 choose 0 times 0.1 to the power of 0 times 0.9 to the power of 6, and I get 0.531441. And now I want the probability that x equals 1. So that's 6 choose 1 times 0.1 to the power of 1 times 0.9 to the power of 6 take away 1, which is 5. Go to my calculator, type this in. 0.1 to the power of 1, 0.9 to the power of 5, and I get 0.354294. So now the probability of x being less than or equal to 1 is the two added together. So 0.354294 plus 0.531441, and that gives me to three significant figures 0.886 to three significant figures. Cool. And then we have part C. Find an estimate for the number of boxes that contains less than 2 defective pens. So Suki has 125 boxes of pens. So less than 2 defective pens. So the probability that x is less than 2. Well, that's exactly the same as the probability of x being at most 1. So what you're going to do is you're going to take your probability, 0.886, and you're going to multiply it by 125, and you get 0.886 times 125. You get 111 pens. Correction, not pens, boxes of pens. Cool, next question. Hickey has a biased die. The probability that the die will land on 6 is 0.2. Hickey is going to roll the die 5 times. Work out the probability that the die will land on a 6 exactly 3 times. Okay, so the probability of success is the probability of landing on a 6. So I'm going to start by saying x equals number of times die lands on 6. And what does it say? It's going to be rolled 5 times. So x is binomially distributed with 5 trials, and the probability of the die landed on 6 is 0.2. We're now trying to find the probability that the die will land on 6 exactly 3 times. So the probability of x equaling 3. Remembering that the formula is the probability that x equals n choose x times lowercase p, probability of success to the power of x, times the probability of failure, q, to the power of n take away x, where q equals 1 minus p. So the probability of x equaling 3 is 5 choose 3 times 0.2 to the power of 3 times 0.8 to the power of 5 take away 3, which is 2. You then type that into your calculator. 5 choose 3 times 0.2 to the power of 3 times 0.8 to the power of 2, and you get 0. Does it want 3 decimal places? 0.051 to 3 decimal places. What do we have then? Work out the probability that the die will land on 6 at least once. So working out the probability of x being at least once, so greater than or equal to 1. That's just the same as, what's the only thing we don't want? We don't want it to equal 0. So 1 minus the probability of x equaling 0 is what we're looking for. You could also write less than or equal to 0, which is just the same as equaling 0, because discrete distributions can only take whole number values from 0 onwards. So now let's find the probability of x equaling 0. Well, we know we've got 5 trials, 5 choose 0, times the probability of success, 0.2 to the power of 0, times the probability of failure, 0.8 to the power of 5. You then go to your calculator and type that in, and I got 0.32768. But what does it want it to? It wants it to 3 decimal places, but we also remember we have to do 1 minus 0.327 ... And when you do that, you get 0.672 to 3 decimal places. And those are ways binomial distributions can be asked with words.